Any queries regarding the previous lectures? I have started the recording, so in a couple of minutes I'll start. I have given you an assignment in Moodle. If you do not have a Moodle account yet, please send me an email so that I can inform our Moodle help desk team. All right, so let us start. So last time we had started an analysis which will predict the performance of the pump. And this again is a simple inviscid analysis, but now we will use global balance of angular momentum or momentum. So we'll consider the momentum about the axis of rotation of the impeller, which is indicated in this figure by this plus sign here. Okay. So we consider the system or material region, the chunk of fluid which occupies the control volume which has been indicated in dotted lines at time instant t. So I've given you two views. So these are engineering diagrams. Okay. This dotted circle here is the inlet of the impeller region. Okay, or the outlet of the eye. The eye is the central part of the impeller. And this dotted circle over here is the outlet. So the flow is three-dimensional. So it will enter in the direction perpendicular to your screen through this big circle. Then it will turn and it will go out radially. And while the fluid particles are moving through this passage between the veins. So this blue lines of the blue curves of the blades or veins. It will acquire a tangential velocity. So in this figure, I've shown the direction of rotation as being anti-clockwise. And the view on the right is a section through an impeller. So what we have is an annular control volume here. And that control volume on this side is shown in dotted lines here. So this surface here is adjacent to the solid surface, and you have air on the left, air on the right, air above. But if you look at this dotted line here, you have liquid above and liquid below. Okay. And the width of the impeller is B1 at radius r equal to r1, which is the inlet to the impeller region. And the width of the impeller is B2 at r equal to r2, which is the outlet. So if I apply global balance of angular momentum about this center point, and of course angular momentum is a vector, so we look at its component in the z direction. So then it is given by ddt of this integral, where you're looking at the radius from the center, from this plus sign to a point somewhere here, multiplied by the v theta component. So if you have a particle at a radius r, which is lying between r1 and r2, and if its tangential velocity component is v theta, then r v theta into dm, which is rho dv, is the angular momentum integrated over the material region. This will be the sum of the moments about the z-axis. Now, if you use Reynolds transport theorem, then this integral over the material region we can write as this unsteady term and this flux. So let us look at the unsteady term. So for the timing now, I've written Reynolds transport theorem in a stationary frame. So del t of this quantity may not be 0. So the flow will be unsteady in the stationary frame of reference. So now, is this integral equal to 0? Well, we cannot say it is immediately that it is equal to 0. It could be positive, it could be negative, it could also be 0. When will it be 0? Well, if you have a function which has positive and negative values over the domain in which you are integrating it, if the positive area and the negative area cancel out, then it could also be 0, even if the function is not identically 0 everywhere inside. Okay, but here it is clear that it is not 0 everywhere inside. Okay. Any queries? Okay. Now we'll look at the transformation which we considered last time. We will consider a rotating coordinate system. So the rotation is about the z-axis, and we have in this plane the axis OX and OY, which are the fixed axis, and the rotating axis OX prime, OY prime. Okay. So let this axis rotate with the angular speed of the impeller, which is the same as this omega. Okay. Then in that rotating frame, the flow will be steady. And the relation between the prime quantities and the original quantities are as shown here. Only differences in the angular variable, angular coordinate. Now, if you use the chain rule, you can show that del del t is del del t prime minus omega del del theta prime. And here the flow will be steady in the rotating frame. So del del t prime will be 0. So first term on the right hand side of equation 5 will be 0. Second term may be non-zero. Now del del theta prime and del del theta are the same. So we can write this del del t as minus omega times del del theta of r v theta. And this you expect to be non-zero. It could be 0 at certain points, but not 0 everywhere. What we want is the integral of this over the volume. So using equation 8, I can write it as the integral over omega del del theta of this quantity. Now look at this quantity. Omega is a constant. Okay, so omega can be moved inside the derivative. And since it's a partial derivative, I can have an extra r inside and divide by an r. Okay. So if we have a vector field whose radial component is 0, axial component is also 0, but the tangential component is this quantity rho times r times b theta times omega r. Okay. So if you multiply it by e theta, it gives you the vector. If you take the divergence of this vector field, you'll get this. So therefore, this unsteady term one can write as integral of divergence of this quantity. And now we can use the Gauss divergence theorem and write it as a surface integral over the control surface. So you'll have rho r v theta omega r e theta dot n. Okay. Now what is e theta dot n? You can see that it is 0 everywhere. Let me go back to that figure. So on this dotted circle, inside circle here, at r equal to r1, the normal is minus er. And er and e theta are at right angles. The angle between them is 90. So the dot product will be 0. If you look at this outer circle here, the outward normal is pointing radially outwards. So that is er. Er dot e theta will be 0. And if you look at this surface here, your normal is Ez or minus Ez. Okay. So Ez dot e theta again is 0. Similarly, these two we have already seen. Here also the normal vector will have a radial component and then axial component, but no tangential component. So the scalar product with e theta will be 0. So this divergence then, which is equal to the surface integral, since e theta dot n is 0, this integral will be 0. So although del del t of rho r v theta is not 0 everywhere inside the domain of integration, the integral value turns out to be equal to 0. So therefore, if you look at the Reynolds transfer theorem, here the first term will
Hello.
Muted, we can't hear you.
Sir, you have been muted. Hello, sir. You have been muted.
okay.
Yes, sir, you are audible.
Okay, thank you. Okay, so this inner circle we'll call del R1, this outer circle we'll call del R2, and the remainder we'll call del R minus del R1 minus del R2. So let us look carefully. Okay, on the remainder, V dot n will be 0. So V dot n is 0 on parts of the control volume other than should be circles. I wrote section here by mistake, 1 and 2. Okay, so only the integral over del R1 will be non-zero and integral over del R2 will be non-zero. And V theta is always positive, but V dot n is negative on del R1 and positive on del R2. So this also should be positive. Okay, so you will have a plus minus sign here and a plus sign here. Actually, I copied and pasted from another file and I forgot to change. This should be plus. Okay, I'll correct it before I send it to you. So on the surface 1 or del R1, the radius is R1 and V theta will be V theta 1 and the outward normal is minus VR. So V dot n is minus VR, which is negative. So this is an inlet. So if I look at this quantity and assume that R V theta doesn't vary over this surface, it will be then the constant value rho into R1 into V theta 1 into V dot n dA. So the area is 2 pi R1 V1. Let me go back and look at that figure again. So this area here is this area. Okay, so width is B1 and the circumference is 2 pi R1. And fluid will be moving in radially through this. So VR1 into 2 pi R1 into B1 is the flow rate in here. And here, and the outward normal here is pointing radially inward. So that is minus CR. So V dot n is negative. So that means fluid will enter the control volume through this. So I marked this as inlet. And this is the outlet. The outward normal is pointing radially outwards. Okay. So on this surface, it is pointing outwards here. And the surface area is the circumference, which is 2 pi R2 multiplied by V2. So I can write it as Q1 flow, where Q1 flow is the volume flow rate through surface 1. Okay, which is 2 pi R1 V1 into VR1. Similarly, in section 2, you have a similar analysis. The only thing is that V dot n at on surface 2, this should be surface. Okay, is plus. Okay, so if I call it Q2 flow, is 2 pi R2 V2. But the global conservation of mass will tell you that the Q flow 1 and Q flow 2 are the same, and that is the flow rate through the pump, which I can simply call Q flow. So if you look at the net efflux of angular momentum from the control surface, then if we go back over here, you will have minus rho Q flow into R on V theta 1 and plus rho cube flow into R2 V theta 2. So if you factor out the mass flow rate, which is rho cube flow, then you have the difference R2 V theta 2 minus R1 V theta 1. So this is the net efflux of angular momentum. So if you substitute back into that angular global balance, you will have the torque on the impeller is equal to the mass flow rate into R2 V theta 2 minus V theta 1. A very simple relation. Now, quite often, authors of fluid mechanics textbooks will use the symbol V with the subscript T instead of the symbol V theta. So this refers to the tangential velocity component or the swirl velocity component. And instead of using small v with the subscript r, they use capital V with the subscript n for normal direction. So this is the component of the velocity normal to the circular surfaces. And we'll also use the symbol capital U to be omega r. So this is the speed of a point on the rotor. So if you look at the velocity of a point on the impeller surface, we'll call it the vector u. It will be the scalar u into e theta. So it is omega r into e theta because this is rotating. Or if you want to write it in vector form, you can show that this is the angular velocity vector cross r. Now, if you want the velocity at a point on the tip of the impeller, which is at r equal to r2, we'll call it u with the subscript 2. So the speed there is omega r2 and the velocity will be u2 into e theta. And if you look at the velocity at a point on the impeller, but at the base where r equal to r1, we'll call the vector u with the subscript 1. So it is the speed u1, which is omega times r1 into e theta. So this notation I am introducing now, and if you want to find the volume flow rate for solving problems, you can use one of these four relations. So the flow rate, if you want to find from the suction pipe side, if ds is the suction pipe diameter and vs is the liquid velocity in the suction pipe or inlet pipe, it is the cross-section area of the pipe, pi ds squared by 4 into vs. Similarly, if you say do is the diameter of the outlet pipe, the outlet pipe is also referred to as a delivery pipe or discharge pipe. And if v subscript o is the liquid velocity in the outlet pipe, then you have an analogous expression for the volume flow rate. So the same flow rate will flow through the suction pipe and the discharge pipe. And this we have already discussed, the flow rate through the circular surface 1 and the circular surface 2. Here I have introduced the notation Vn1 and Vn2. So subscripts 1 and 2 refer to the circular surfaces 1 and 2. So depending on the data given in the problem, you can use one of these four relations to find the volume flow rate. Now let us look at what are called Euler's equations of turbo machinery. So we have already found the torque is equal to the mass flow rate into R2. Now here I've rewritten that expression using the symbol capital V with a subscript 2. So R2 into the tangential velocity at 2 minus R1 into the tangential velocity at 1 multiplied by the mass flow rate, which is rho q, is the net efflux of angular momentum through the control volume, and this is the torque on the impeller. And the power then will be T omega. So if I multiply each side of equation 39 by omega, okay, and move the omega inside, you have omega R2 Vt2 minus omega R1 Vt1. But omega R2 we can call U2, and omega R1 we can call U1. And here U1 is not equal to U2. In fact, U1 will be less than U2. Okay. So this is the power that will be produced. Sorry, the power that will be transferred from the fluid to the fluid from the impeller. But we have also shown using thermodynamic equations that power is rho Q GH, where H is the what you call the head developed by the pump. So if I look at equation number 41 and 42, the rho Q is common. So you have GH equal to U2 VT2 minus U1 VT1. And this is sometimes called energy transfer. We are calling it E. It is the energy transfer per unit mass per head. So it is simply P divided by rho Q flow. And if I divide by G, then I get the head developed by the pump in units of meters. So the head developed by the pump is U2 VT2 minus U1 VT1 by G. So these expressions, all of them, the one for the torque, one for the power, one for the energy transfer, which is equivalent to the power, okay, and another for the head. These are all sometimes called Euler's equations of turbomachinery. So this is using simple one-dimensional analysis. All right, now we'll try to find the head discharge characteristics for ideal fluid flow. So I've given you here an enlarged view of the impeller. Okay. So I've shown just one impeller which is rotating anti-clockwise. And the region of the impeller will be from R equal to R1 to R equal to R2. So if you look at the velocity triangle at the outlet, the relative velocity will be tangent to the blade. This we have discussed before. And the U2 vector will be perpendicular to the radial distance. So if I look at the center of rotation, and from this if I draw the radial line up to the tip of the impeller and extend it here, the vector U2 will be perpendicular to that line. And the direction will be from this point to this point because I've shown the impeller rotating in the anti-clockwise direction. So the relative velocity W2 at point 2 plus the rotor velocity at point 2, which is U2, will give you the absolute velocity V2 at point 2, which is the outlet of the impeller. Now the angle between V2 and U2 is what we are calling alpha. And the angle between W and minus U, so if I look at minus U, the arrow will point this way. So when both the arrows meet at a point, this angle will be the blade angle, which we call beta 2. And similarly, I can draw here the velocity triangle. So now this is at the design condition. So when the pump is running and the design condition, the relative velocity at the inlet will be, this vector will be tangent to the surface, impeller surface here. So this is W1. And U1 plus W1 will give you V1. So in this figure, U1 is perpendicular to the radial line joining this point 1 and the center of the rotation, center of rotation of the impeller. Okay. So U1 plus W1 will give you V1, the approach velocity. So the absolute velocity of the liquid approaching the impeller will be in this direction if the angle here is less than 90. Okay. So alpha 1 is the angle between the vectors V1 and U1. And beta 1 is the angle between the vectors W1 and minus U1. Okay. But this is only at the design condition. And the normal component of velocity is, if I look at this vector here, its tangential component is this small one, okay, Vt1, and Vn1 is this perpendicular distance from this point to this base of the triangle. Similarly, if I look at here, if this is a vector V2, I can resolve it into a normal component which I am calling Vn2. So this is the same as Vr2, and a tangential component which is Vt2. Now, we are going to use, for simplicity, an inviscid model. So when the fluid is inviscid, there is no swirl at the inlet, R equal to R1. Now this is a point which is not explained in the books. So I'll spend a little bit of time in explaining it to you. Now, look at this case here. The fluid will enter axially and then it will turn. Okay. Now, in the eye of the impeller, okay, the fluid can be set in tangential motion if it's a viscous fluid. But that mechanism is through the no slip condition. So when the rotor is rotating, the fluid particle which is adjacent to this surface here at r equal to r1, it will be dragged along by the solid, okay, and it will send the next layer of fluid into motion and so on. But if it's inviscid, the no slip condition doesn't apply. So there will be slip at the surface. So surface will rotate, it will not drag the fluid in. And at the inlet, the fluid is axial, it has no swirl. So the fluid will not acquire any swirl until it enters this region, in this space. So once the fluid enters here, the impeller blade, by pushing on the fluid and producing a velocity component, relative velocity component normal to this surface, it will generate swirl. So at this location r equal to r1, in most cases, if you say the model is an inviscid model, the v theta 1 will be 0. But at the outlet, there will be a non-zero v theta. So v theta is not generated by the no slip condition, it is by the no penetration boundary condition. All right. So now, if you say that there's no swirl, then Vt1 will be 0. Okay. That means your alpha 1 will be 90 degree. And this V1 will be in the radial direction. Okay. So we will have Vt1 equal to 0. Equivalently, alpha 1 is 90. And Vn1 is the same as, which is equal to Vr1 is the same as V1. The speed of the velocity, speed of the liquid at r equal to r1. Okay. So now if you go back and look at this relation for the head, if we say Vt1 is 0, okay, then the head will be simply U2 times Vt2 by G. So head for an inviscid model will be U2 into Vt2 by G. So this is meter per second, this is meter per second. So if you multiply it together, you have meter square per second square. And you're dividing by G, which is meter per second square. So it will give you the head in meters. Okay. Now let us look at the velocity triangle at the exit. Okay. So if I look at tan of beta 2, it will be Vn2 or Vr2 divided by, sorry, it will be W2, Wn2 by Wt2. If you look at this right angle triangle here, okay. But you see that W2 radial component and V2 radial component are the same. Okay. But if you look at the tangential component, W2 is actually U2 minus of Vt2. Okay. So U2 is this entire length, Vt2 is this length. U2 minus Vt2 will give you Wt2. Okay. So tan of beta 2 is Wr2 by W theta 2, which is Vn2 by U2 minus Vt2. So I can use this relation and write this as U2 minus Vt2 by moving this denominator, this expression in the denominator here to the numerator here, and dividing by tan beta 2, which I can write as cot beta 2. So from here, if I move Vt2 to the left hand side of the equation, you see that the swirl component of the fluid velocity at the outlet of the impeller is U2 minus Vn2 into cot beta 2. This is from one-dimensional analysis. So if I take this and substitute into the expression for head, you will have U2 by G into U2 minus Vn2 cot beta 2. So I can write it as U2 square by G minus U2 into Vn2 cot beta 2 by G. But now Vn2 I can express in terms of the flow rate. You flow by the flow area at section 2. which is 2 pi r2 v2. Okay, so if I substitute this over here, you have h is u2 square by g minus u2 multiplied by q multiplied by cot beta 2 divided by 2 pi r2 v2 g. Now I can express u2 in terms of omega. So you have omega r2 whole square over here. And here if I write omega r2, the r2 in the numerator and denominator will cancel out, and you'll get omega divided by 2 pi v2 into cot beta 2 by g into q. Now the pump will be run by an electric motor, which will run at a synchronous speed. So the speed omega, angular speed, will be constant. So the first term will be constant here, and the blade angle of course is constant, v2 is constant. So this slope here of the curve will be constant. So you see that when omega is constant, the relation between h and q is of the form some constant a0 minus another constant a1 into q, and a1 is this quantity. So when the angular speed is constant, ideal flow theory is showing you that the relation between h and q is linear. Okay. Now when q is 0, there will be a head produced, which is simply a0, and a0 is simply r2 square omega square by g. So in this case, the liquid inside the pump will be just churned, swirled, and there will be a pressure difference, measurable pressure difference between the inlet of the pump and the outlet. But if I close the delivery valve, there will be no flow in the discharge tube. There is no flow in the inlet or suction tube, but the whole pump is immersed in water. There is water inside the pump, it will just rotate, and you'll get a head which is called the shutoff head. Now, the blades could be curved in different directions. So I have three diagrams here. In all three cases, the impeller is rotating in the counterclockwise direction. The middle figure here, the blade is radial at the exit. So this is called a radial blade. And here, in all cases, I am drawing the velocity triangle at a point where the radial line is vertical. Okay, so that if you look at this tip of the rotor, the velocity of the solid at this point is horizontal, and the vector will point from left to right. So if omega is the same, the length of this vector will be the same. Okay, but here the fluid will move out radially, so the relative velocity is w2. Okay, so the angle beta is 90. Now if the angle is more than 90, this will happen if the blades are curved in the forward direction, forward or backward relative to the rotation, direction of rotation. So the figure on the left is an example of what you may call a forward curved blade or forward facing blade. So the curvature of the blade is in the direction of the rotation. And as you can see here, if you look at the angle between W2 and minus E2, this angle beta 2 is then more than 90. And the figure on the left, extreme right here, is a case where again the impeller is rotating counterclockwise. The blade is curved backwards in the direction opposite to the direction of rotation. So if I look at this relative velocity vector W2, the angle between W2 and minus E2, this beta 2 is less than 90. So for a radial blade, at the exit, beta 2 is 90. For a backward curved blade or backward facing blade, beta 2 is less than 90. And for a forward facing blade, a forward curved blade, the angle at the exit, the blade angle at the exit, beta 2 is greater than 90. Okay, now if you go back and look at the slope of the curve, dh dq, it is proportional to this. This is a constant, of course, which will depend on the angular speed. But the speed is constant, as I said, because it will be run by a synchronous motor. V2 will be a constant. It depends on the design of the impeller. Beta 2 is another constant. It depends on the design of the impeller. But this beta 2, suppose is 90. That is the middle case here, the radial blade. If beta 2 is 90, tan beta is infinity, tan 90 is infinity, and cot 90 is 0. Okay. So then if I plot H versus Q with omega constant, you will get a horizontal line. The head will not change with Q. Now suppose beta is greater than 90. Okay. Then what will happen? Tan and cot will be negative, and there is a minus sign outside. So this slope will be positive. So the head will increase linearly with increase in the volume flow rate Q. So here I have not written the superscript flow here. Okay, for brevity. And if beta 2 is less than 90, okay, then of course tan and cot will be positive, and there is a minus sign here. So the head will decrease linearly with Q. So this is the prediction of ideal flow theory. Okay. So let me go down and look at the actual HQ characteristics. So the actual head will be the ideal head minus losses. Now losses you can characterize as hydraulic losses, leakage losses, and mechanical losses. So the mechanical losses will be due to friction at the bearings. Okay. And here leakage loss I'll explain. But first let me talk about hydraulic losses. This again may be categorized into a friction loss, a circulation loss, and something which is called shock loss. Now this shock is of course in the context of turbo machinery is not the same as shock in the context of a compressible flow. Now let us look at what we call circulation losses. Now we are assuming the flow to be one-dimensional. This is true if you have infinite number of vanes, so that the gap between the adjacent vanes is infinitesimally small. Okay. But in reality, you will have finite number of vanes, and if this is one impeller and this is the adjacent another adjacent impeller, you have a space in between where the flow may not be one-dimensional. Okay. Now here I have shown three impellers, three adjacent impellers, and you have here this is the eye. Okay, the shaft will be rotating as shown here in the anti-clockwise direction. So this impeller will, when it rotates, it will push the fluid. So if you look at the fluid which is immediately adjacent on the upper side here, the pressure will be high. So this is what I have indicated by the plus signs here. So this is called the pressure side of the blade. It's also called the leading side of the blade. And the other side is called the trailing side of the blade. Here what will happen is when the impeller rotates, it will try to create a vacuum, but there will be no vacuum because liquid will rush in. Okay, but the pressure here will be less because the fluid will rush in here, and here the pressure is more because the solid is pushing the fluid. So the minus signs here indicate that the pressure is low. So there is a pressure difference between the leading side of the blade and the other side. Okay. So the lower side of the blade we can call the suction side here. So this is another blade. So the plus signs indicate that there is high pressure here on this side of this blade and low pressure here on this side. So I've used different colors here, the red for this middle blade, green for this blade here. Now look at this region in between here. There's high pressure here and low pressure here. All right, so the flow will not be one-dimensional. There may be some, relative to the rotor, there may be some recirculation here inside, which we are not accounting for in this simple analysis. So that is not a viscous, even an inviscid analysis with finite number of vanes will be much more complicated, and it will show you a multi-dimensional flow. Okay. But what we have assumed is one-dimensional flow that can be justified if the number of vanes is infinite and the gap is very, very small. In that case, at each point inside here, the direction of the relative velocity will be tangent to the blades. Okay. But here, On this surface, if it's invested, the relative velocity will be tangent to the blade. On this surface, it will be tangent to the blade, but in between, we don't know in which direction the relative velocity vector will point. Okay. This is what we call circulation losses. So this can be predicted using a more sophisticated inviscid analysis. And of course, there will be friction losses because there will be drag on the blades. Okay. The other important thing is what we call shock loss. Okay. So I've been talking about design condition or design flow. As I said, the fluid will enter radially at the impeller at the radius r equal to r1. The reason being that an inviscid model predicts that there is no swirl. Okay. Now, in the design condition, the relative velocity vector will be tangent to the surface of the blade. So the angle between W1 and U1 is beta 1, the blade angle, but only in the design condition. Now, suppose you have a case where the angular speed of the pump is constant. That will be the case because it is being run by a synchronous motor. So then, of course, I am drawing the velocity triangle at a point where the radial line, so the tip of the impeller, not tip, base of the impeller is vertical. Okay, so V1 is vertical in all the three case diagrams here, and U1 is horizontal, and the magnitude of U1 is the same. It is R1 times omega. So in all three cases, U1 is the same, omega is the same, but what is different is the flow rate. Okay, so suppose relative to the middle case, I reduce the flow rate, then the radial velocity will reduce, and radial velocity is actually V1. So we'll have a smaller triangle over here, okay, compared to this middle triangle. So this vector tangent, relative velocity vector W2 will not be tangent to the surface. Okay, it will move towards the underside of the blade, which you may call the suction surface. So some eddies will form over here. There will be turbulent flow here. Now suppose the flow rate is more than the design flow rate. Then you will have a triangle which is larger here. Okay, this V1 is larger. Now you see again the relative velocity vector will no longer be tangent to the surface, but the flow will go towards the pressure side, pressure surface here, or leading surface. Okay, and there will be eddies formed on the upper surface here. So when the flow rate is less than the design flow rate, eddies will form on the lower surface here, and when the flow rate is more than the design flow rate, eddies will form on the upper surface. So we'll say that the middle case is a no shock condition, and the left case and the right case here, depicted by these two figures on the left and right, these are the cases with shock. Okay. So if I say beta 1 prime is the actual angle between W1 and U1, then in the design flow condition, beta 1 is the blade angle beta 1. And here beta 1 prime is less than beta 1. Okay. And here beta 1 prime is greater than beta 1. Okay. So in the case on the left and the case on the right, there will be what we call shock losses due to turbulence formed by the eddies. Now leakage loss takes place because the fluid will enter axially here, parallel to the axis of the pipe, inlet pipe. It will turn and will go out, and it will be collected in the scroll case as we discussed yesterday. But the pressure here is high compared to the pressure here. So some liquid will leak back here between the casing and the blade. So if I call this small q, okay, and if I say Qi is the flow rate of the impeller, then Qi plus Q is Qi minus Q is the flow which is collected by the scroll case. So Q, the actual flow rate, is less than the flow rate to the impeller. So this is what is called leakage losses. So now if you look at the theoretical curve, if it's a backward curved blade, it will go down like this. Okay, and because of the circulatory flow, the actual head will be less. Because of friction, it will tend to go down like this. Okay, and if you look at the shock loss, if Q is the Q design, there is no shock loss. But if Q is less than Q design and if Q is more than Q design, there will be loss due to the formation of turbulent eddies. Okay, so the actual curve will be have a shutoff value which is much less than the theoretical value, almost 50% or 60% of the Euler head. It will increase to a peak and then it will decrease. Okay. Now let me go back. So I'll just mention for the time being that a forward curved blade can cause a condition which is called pump surge. It is an unstable operation where the pump will not run in a steady condition. So I'll explain this pump surge in detail in the next class. Okay, today I'll just mention that this occurs when the blade is forward curved. So backward curved vanes are preferred. So that is why when talking about the actual curve, I've started with a drooping characteristic here for the theoretical curve, which is typical of a backward curved vane. All right, now let us look at a concept called net positive suction head, sometimes called NPSH. So N for net, P for positive, S for suction, H for head. Now, in an actual situation, you will have a pump and you will have a network of pipes. Okay, so you'll have a delivery pipe and an inlet pipe or suction pipe. So it is like you can consider an analogy with an electric circuit. Okay, so here you may call it a hydraulic circuit. Okay, so if you look at different points in the hydraulic circuit, there will be points where the pressure is low and points where the pressure is high. Now the pump is increasing the pressure, so the maximum pressure will be at the outlet of the pipe. So just at the exit of the pump or the inlet to the discharge pipe, you will have the maximum pressure. And as the fluid flows through the discharge pipe, the pressure will drop due to friction along the pipe. So the same fluid will return back through the suction pipe into the pump. So the low pressure point, the lowest pressure will occur on the inlet side or suction side of the pump. And if this pressure is below the vapor pressure, then cavitation might occur. Okay. So you want to look at conditions under which cavitation does not occur because you want to avoid it. So this quantity, net positive suction head, is defined as the inlet stagnation pressure minus the vapor pressure by rho g. And stagnation pressure, you know, is the static pressure plus half rho v square. Okay, so if you divide by rho g, you have the static pressure head and the velocity head minus the vapor pressure head. So this is what you call net positive suction head. And this must be greater than some minimum value. Okay, so that cavitation does not occur. So if this NPSH falls below a critical value, some minimum value, then cavitation will occur, which is undesirable. So here the subscript STAG refers to stagnation pressure. The subscript VAP refers to vapor pressure, which will depend on the temperature of the liquid. And of course also its chemical composition. And the subscript inlet is the inlet velocity. V inlet is inlet velocity and P inlet is the inlet pressure. Okay. Now we can keep this middle term on the one side of the equation and move the other terms to the other side of the equation. Then we can write V inlet whole square by 2G equal to NPSH plus this difference between the vapor pressure and the inlet pressure. Now, what is the minimum inlet pressure that you can allow such that cavitation does not occur? Well, that is the vapor pressure. So if I set P inlet equal to 0, P inlet equal to P vapor, then this second term on the right hand side here will be 0. And you will have the maximum possible kinetic energy at the inlet when cavitation is imminent. Cavitation imminent means inlet pressure is vapor pressure. V inlet square by 2G maximum value is NPSH. Now what will happen is P inlet is larger than P vapor, this will be a negative quantity. Okay, so the inlet velocity will be less than this value when cavitation is imminent. So the net positive suction head is the head required at the pump inlet to keep the pump from boiling. Okay. So if you have installation as shown in this figure, this is the upstream reservoir which is called sump, and you have air above here, and this is a simple sketch of your centrifugal pump. This is the discharge pipe. So consider a streamline starting from the surface here, which I've called point 1, into the suction pump to a point 2, which is the location of minimum pressure near the inlet. Okay, so this is near the eye of the impeller. Okay, so this is the point which is the inlet to the impeller region. Okay, now you can apply the energy at the downstream point 2 equal to the mechanical energy at point 1 minus the loss term, head loss term. Now P1 is atmospheric pressure, and if the tank is large, the surface area at this section here is large, so you can neglect V1 here. So this is first term on the right hand side will be P atmosphere by rho g. This will be 0. Okay. So you'll have P2 plus V2 square by 2G plus Z2 is equal to P atmosphere by rho g plus Z1 minus head loss. Okay. Now NPSH is defined as the sum of these two terms, P2 by rho g plus V2 square by 2G minus the vapor pressure head. So I can use this expression and write it as P atmosphere, looking at this term, minus this vapor pressure by rho g, and then I can write plus Z1 minus Z2, which I am calling minus delta Z, minus the head loss. So this delta Z is the difference in elevation between the point of minimum pressure here and 1. So in this case, delta Z is positive. Okay. The pump is above the surface of liquid in the sump. Delta Z could also be negative if the pump is submerged below the surface of water in the sump. Okay. So if delta Z is positive, on the right hand side here, you have a negative quantity, and the head loss also will be positive, so we have a minus sign here. So this whole quantity on the right hand side must be larger than some minimum value. So this head loss includes the major loss in the suction pipe, and the other losses we may refer to as minor losses. So there may be a strainer and a check valve or foot valve. There may be some bends. So there may be further losses here. So this quantity which we found here, this right hand side here, must be greater or equal to some minimum value, which will depend on the operating conditions of the pump. And sometimes people define a net positive suction energy, which is simply G times NPSH. But more importantly, there is a parameter referred to as the Therma cavitation parameter, named after Therma. Most authors use the symbol sigma to denote this quantity. It is the NPSH divided by the head developed by the pump. Okay. Now NPSH we have shown for this application to be the difference between the atmospheric pressure and the vapor pressure in units of meters minus this delta Z minus the head loss. Okay, so this quantity must be a positive quantity here, and from that we can subtract delta Z and head loss. Okay, so there is a critical value of this thermal cavitation parameter at which cavitation will start to occur. So if sigma is larger than sigma critical, then there will be no cavitation. Cavitation will not occur. Okay, so you have to ensure that sigma is greater than sigma critical. But if you look at the expression for sigma critical here, you have a head loss term which will reduce the numerator, and you will have this delta Z which will reduce the numerator value. So the larger the delta Z, the less will be the numerator. Okay, so you have to ensure that delta Z is not too large. If delta Z is very large, then this will fall below the critical value. Okay, so you may need to decrease the static suction lift. So the suction lift means the distance, vertical distance through which the fluid is lifted from the surface of the sump to this inlet of the pump. Okay, the point of minimum pressure here. This is on the suction side of the pump, so it's called the suction lift. Now in some cases you may want that delta Z be negative. If delta Z is negative, that's good for you because it will increase the value of the numerator and ensure that sigma is greater than sigma critical. So if you are unable to make this quantity on the right hand side larger than sigma critical, okay, in an application, then you have to submerge the pump. So the pump has to be below the level of water in the reservoir. So delta Z then should be negative. Okay, so this is required when the inlet pipe is very long. If you have a long inlet pipe, then this head loss term will be large. So if you're subtracting a large quantity from this difference between atmospheric pressure and vapor pressure here, okay, then sigma will be small. Okay, in that case you may want delta Z to be negative. Okay, so it is almost 6 o'clock, so I'll stop here. Now we have been given additional slots, as you may be aware. Has Professor Das talked about the additional slots? We have one slot on Friday evenings.
Sir, like Professor Das said that he will take that this week.
Professor Das will be taking the class in that slot, right?
Yeah. Yes.
Okay. Now we have another slot on Saturday afternoons from 2 to 3:30. Okay. Now we have another 4 classes left if I just take the normal classes. Okay. But that will move you towards the end of the semester. If you want, I can take one slot if possible on this Saturday so that I can give you one slot free at the end.
Yes, sir. Okay.
So
Sir,
once
actually,
I finalize that, I'll discuss with Professor Das and send a mail to you through ERP. Okay.
Sir, this weekend, sir, we have to work on our BTP. We have the submission. So can you keep it next week instead of this week?
Oh, okay. But it so happens that next Saturday will be Diwali.
Oh.
Oh, but when do you have to submit the BTP?
Sunday.
On Sunday.
Yes, sir.
Okay. Sunday, at what time do you have to submit?
So like it is the last day. So by night we can submit.
Oh, by night. Okay. All right, then we'll, if necessary, then we'll. Can you give me 1 hour on a Diwali day? We'll see. Okay, I'll give you time for your BTP, man.
Yes, sir. Thank you, sir.
Okay. All right. Are there any queries?
Yes, sir. Yes, sir. Like we did that angular momentum conservation, right, for the centrifugal pump.
Pardon?
We did angular momentum conservation for centrifugal pump, right?
Yeah,
In
yeah,
that we had a stationary reference frame.
yeah.
And
Otherwise,
like what
you will
happened to
have
the
to have.
unsteady term?
Okay, let me go back.
Yes.
Yeah, this equation. There is an unsteady term and there is a flux term.
Yes, sir. Yes, sir.
Now,
We dealt with the flux term. What about unsteady term? Yeah.
okay, so I have evaluated the unsteady term and shown that although the del t is non-zero, the integral is 0. See, del t we wrote as del t prime minus omega del theta using the chain rule.
Yeah,
Okay.
yeah, yes, yes.
And del t prime is 0 because the flow is steady in the rotating frame.
Yes, sir.
Okay.
Yes.
So you have del t is minus omega del theta. Okay.
Yes, sir. Yes, sir. Yes.
And this quantity here I
Yeah,
wrote as
we can do that. Yeah.
the
Yes, sir.
divergence of this vector field. Okay.
Okay.
So using the Gauss divergence theorem, I integrated this. Okay.
Over a surface.
Right.
Yes, sir.
And it so happens that for the control volume that we have chosen, E theta dot n is 0.
Okay.
Okay.
Okay. Yes, sir. Yes, sir. Okay.
Now, this is a very important point. See, most books will simply ignore this explanation that I've given you. Okay.
Yes, sir. Yes.
Another point is that suppose you have infinite number of vanes, then del L theta will be 0. So del L theta will be 0 if you have infinite number of vanes. Okay.
Yes, axisymmetry, right?
Okay.
Yes.
So that is one way of looking at it. But
Okay.
if you want to do a CFD analysis, you would use a rotating frame because it will be easier to apply the boundary conditions. Okay. In that case, del L theta will be non-zero. Okay. So I am trying to bridge the gap between the advanced analysis and simple analysis. Okay. By giving
Yes,
you
sir.
this extra detail here, which I worked out. And I've shown you that although del L t is non-zero, the integral is 0. This can happen if del t has positive sign and negative sign. Okay. Now, an
Yes, sir.
alternative viewpoint I can give you. I'll stop sharing this, and if you have time, I'll open another document.
Sir, you are muted. Muted. Can't hear. Yes, sir.
Okay.
Yes, sir. Audible. Audible. Yeah.
Okay, thank you. So the form that I've used is this form. ddt of phi system is del t in the stationary frame plus the flux evaluated using the absolute frame. velocity. Now this is always valid. Only problem is sometimes this quantity here is non-zero, this integral. Okay. Now, an equivalent form is you use del L T prime, the temporal derivative in the rotating frame, and then you have to use the flux, evaluate the flux using the relative velocity. Okay. So this can be shown. I have shown it here, but I thought that maybe you will get confused with too much of mathematics towards the end of the semester. But if you're interested, I can leave it to you. I can upload this file. Okay. So if I use the second form here, then straight away you can say del L T prime is 0. Okay.
Yes,
Then
yes.
what you have to do is use the
Relative velocity, yeah.
this W dot n instead of V dot n.
Yes,
Okay.
sir, yes, yes.
Now look at the surface 1, circular surface 1 and circular surface 2. W dot n is either plus WR or minus WR. Okay. But WR is the same as VR. Okay. So if you use the absolute velocity, you get the same result. So it is actually fortuitous. Suppose I make a mistake in my analysis and say that I ignore this term. Okay. And just evaluate the flux using this term. You'll actually get the correct result.
Understood, understood. Yeah, like in the stationary frame, even if we apply, yeah, understood. Yes, sir, yes, sir. Like,
Yeah. So this derivation also I have given you here. It is a similar derivation to what we have done. So del L T, this arbitrary term, del L T is not going to be 0 at each and every point. But the integral value could be plus, could be minus, it could also be 0. We don't know. Okay. So I first write it as del L T prime minus this quantity. Okay.
First term is 0, yeah.
Yeah. The first term on the right hand side will be 0 at each and every point. And this is like a definite integral, so this will be 0. And this quantity I can write as omega.
Yeah, like the same thing we did. Yeah.
Same thing, similar thing. Okay. And here I've given it, I made it look more elegant by using these vectors. Okay.
Yeah, like generalization.
I called omega cross r over here. Okay. So
Yes,
if you use the Gauss divergence theorem, you will get rho phi omega cross r dot n. Okay. So you have this quantity here. And then if you subtract, you add these two.
Yeah, we get V relative.
You get V minus omega cross r, which is W dot n. Okay. So if I look at this temporal derivative in the stationary frame, this term integrated over that volume plus the flux evaluated using the absolute velocity is equal to the sum of these two terms, where the flux is evaluated using the relative velocity, and this is the temporal derivative in the rotating frame. Now this term is definitely 0, the first term on the right hand side of equation 87. Okay.
Yes, yes.
But it so happens for the control volume that we have chosen.
Yeah, left hand side, first term is also 0.
Same, they will give you the same value. And hence, although this del L T of rho phi is not 0 everywhere, the integral is 0. So this can happen only if it has plus values at certain points, minus value at other points, and the positive area and the negative area, if you plot it as an area under the curve, okay,
Yes,
it turns out to be 0.
Yeah, which is validated through this Gauss divergence theorem that we played.
Yeah. So this is a very subtle point which you will not find in any of the books. Okay. So I worked it out, I think, so I shared it with you. Now, you tell me, do you want me to delete this part or include it?
Like in the exam kind of.
I'll include it, but see, as far as the exams are concerned, it is the
straightforward. Okay, yeah, but like deletion is not required from the material, I think.
Should I include it?
In the material, right?
Yeah.
Yes, sir. It will be preferable. Like you could put a star or something like like.
Okay, I'll put a star and say advanced material.
Yeah, yes.
Okay, so you don't have to then. If you don't want,
confusion won't be there. Yeah, yes.
Oh, okay, good. All right. Any other queries? If not, then I'll hang up. I've given you a very simple assignment through Moodle. If you do not have a Moodle account, please let me know.